I'm back working on the number 3 Wren computer system now, and in the previous video in this series I was having an issue with the keyboard. It wasn't reading all the keys, at least it appeared to be a problem with the keyboards, and so I started tracing this through, looking at the keyboard controller and the various support chips. There's basically a latch and a multiplexer that's used to strobe the keyboard. And I thought the problem was in there somewhere, but it turned out to be a bit more complicated than that. And while I was doing this testing, I was going through various test steps, including loading up CPM so I could do a more in-depth test on the keyboard system. And at that point the machine stopped booting and it was failing at test step number 2. Now, test step number 2 is defined as a failure of the video RAM. So I started looking at the video RAM and I couldn't find anything wrong with it. But the architecture of this machine is quite interesting. It's quite cleverly thought out, and I will be coming back to this in a future video to show how to upgrade this to more RAM and how the memory system works in a bit more detail. As always happens with projects like this, I've spent a lot of time reverse engineering this, figuring out where the various ports are and what they do. And a few days ago, a friend who's extremely good at doing the sleuthing and detective work managed to track down some original technical bulletins that were in the possession of one of the original people that worked on the project. Unfortunately, there's not a great deal of technical information, but the information that was supplied is quite interesting and did match what I'd been figuring out with the reverse engineering, which is always very gratifying, and it's what makes these projects so interesting. Would have saved a lot of time, of course, had I had the information up front, but it is quite interesting figuring out how these things work, and I think it's probably more beneficial doing it this way round and then getting the information rather than just having a lot of information to start with, although having said that, a schematic would of course have been useful. As I've said in the past, schematics tend not to exist for very old machines like this, simply because they were never in the format that could be easily distributed. So it may well be that there is no schematic drawing for this that can be easily distributed, and that's one of the reasons why I like to reverse engineer these and create schematics that can be put into a form that can be distributed, so people such as myself and anyone that's got one of these can support them into the future. So without a schematic, as ever, it got a bit complicated trying to sort out what was going on. As you know, I use a thermal camera when I'm doing fault finding on these boards, and had noticed that several devices ran a lot hotter on this board than on the other two boards, and in particular this 244 buffer chip was getting very hot. Now, there are 3 different blocks of memory that are used in the video RAM, and it's kind of configured in a bit of a strange way, but it's even more peculiar during the boot up sequence. And because this looked to be getting quite complicated, I started looking back into the code, and I still want to go ahead with reverse engineering the code, and I will be progressing that project. So anyone that's interested in getting involved, if you can be patient a little while longer, and I will get these files hopefully made available so that you can get started on the work. But it will be very interesting. But what I'm doing at the moment is trying to put a bit more information on the port access file, and I'll be going over that in a bit more detail in the next video and showing really how the system's structured. But for this fault, it was getting a bit strange, and I wanted the machine bootable so that I could do more fault finding and also figure out a bit more information about the structure and the architecture of the circuit. So looking at the code, the way the self-test works, which is of course where it was failing, is there is blocks of code, functions that do certain tasks, and one of those is to test a block of memory, and then it returns an error in the 0 flag of the processor if the test fails, and then that's used to flag with the system that the test for that particular memory block failed. Now, because this system is banked, and it supports up to 16 banks, but not all of them are used, but banks 0 through 3 are used for the common RAM. The video RAM has separate RAM areas for the character RAM and for the graphics RAM. Bear in mind this machine will support color graphics. Not on the inbuilt monitor, of course, but you can plug an external color monitor in. And one of the issues with having banked RAM is if you want to run the self-test from one of the two ROMs, one ROM is in bank 4, one ROM is in bank 8. Rather than switching continuously between the two banks when you're trying to test a block of RAM that's not in the same bank, the way that this system works is it copies the block of code that it wants to run the memory test from into RAM in the bank, in the common RAM. That's the common RAM that's across all banks, and it copies that block of code into that common block of RAM, and then it runs the test code from the copy and not from the version that's in the ROM. That's why I was getting a bit complicated trying to step through the code with the logic analyzer. That's why I'm not showing it on video. It get very involved, and it just looks a bit weird when you're trying to trace it through why it's trying to access code from the RAM area rather than from the ROM. Then it jumps back to the ROM, of course. But the upshot of that is it gives you some fairly strange results, and that was you notice these two ICs are now in sockets, and before they were soldered to the board, and these are two SRAM chips. In fact, the ones that were in there are these two, and they test okay on the EEPROM tester. I've got an EEPROM tester that will test these, and they test fine, but when they're in the board and the self-test was failing, if I swap the crystal from a 12 MHz crystal to a 10 MHz crystal, it would go through the boot up fine, albeit I'd get nonsense on the screen because the refresh rates were incorrect. So it was obviously a race condition of some sort. So I spent a while tracing this around and found out that the TTL levels, the signal levels coming out of the 244 multiplexer chip, it's not a multiplexer, but it's used to multiplex the data bus between the different blocks of RAM. The signal levels were very low, which is why it was getting hot, and they were being pulled down by something. And it turned out they were being pulled down by the two RAM chips. Even though the RAM chips were working, they were putting a big load on the 244 buffer. Now, while I don't recommend this as a technique for normal use, I tested this by piggybacking another 244 onto the back of this. Bear in mind these were soldered to the board at the time. Put the 12 MHz crystal back in, and it booted up fine. Took the piggyback off and it stopped booting again. So in other words, it was a drive level from this particular device. I swapped various different manufacturing versions of the 244 out, and it would actually boot with a couple of the types. But even so, that's not the way it's supposed to work, so there's something wrong here somewhere. So I decided to bite the bullet, and I desoldered the two SRAM chips, put sockets in their place, and sure enough, when I put some replacements in, it's now fine, and the signal levels are almost back to normal. Not quite, there's still something going on here, but I think there's a bit of overlap between two of the buffers putting data onto the same bus, and I think that's a sluggish chip somewhere else. I'll need to track that down. But it is now booting up in the way that it should do. So I'll get this booted up. We've got the freshly restored, repaired floppy drive hooked up, and in theory at least this should now boot up. And the side effect of this was part of this was also interfering with the reading of the keyboard, which is why the keyboard wasn't working properly. So in theory at least now everything should work, and the machine should boot up to the point where we can actually run some programs on it. I won't do that in this video, but I just wanted to quickly cover this off before I move on to the next video, because this was quite an interesting fault, at least I thought it was. So I'll just get this booted up. So we have the welcome screen on the display. Just move the camera across a bit so you can see that. And I'll put the floppy disk into the drive and see if it will boot to the operating system. So as I said, this is the floppy drive that I repaired in the previous video. So I'll move the camera back across, you can see it's starting to do something, and sure enough we have the boot screen back. So what I was getting before, when the fault was showing it was sometimes getting to starting to draw this screen, and then the system would crash and it would write just half the text or do something else peculiar. So what I should be able to do now is run CPM, and as you can see it's now all working fine. I have been running a few other tests and this seems to be a lot more stable than it was. It was just acting in a real flaky way before, and that was obviously because of the contention between the various devices. And as I've said previously, this is one of the problems sorting out machines like this, where components quite often don't just fail, they start underperforming. And in a machine like this, where really 12 megahertz is too fast for this machine to run, it's only 6 megahertz at the processor of course, but even so, trying to run a Z80 at 6 megahertz, especially one of the original Z80s, is a bit optimistic. And I also found that I had to swap the Z80 around and find or try various types before I got one that would work. I do have some CMOS Z80s that are supposed to work up to about 20 megahertz, so I'll be trying one of those in there to see if that makes it even more stable. But that's it for this video. As I say, just a quick video to go over what I've been working on, and again just to test the floppy drive that we'd repaired to make sure that works. And in the next video we'll hook the fluke back up to this and we'll start investigating the architecture of this machine and see if the deductions that we've been making are correct, and if the way that everything's addressed is as we believe it is.